3, 2, 1. Go. We're live. This is Retraice segment number 82 for Wednesday, December 14th, 2022 at 11 p.m. Eastern, 8 p.m. Pacific, second in a doubleheader. Retraice is about what's going on out there. The short answer to that is computer control. We are in the December to Remember Math and Code event in preparation for our deep dive study, January to June inclusive, of AIMA4e, Artificial Intelligence, a Modern Approach, Russell and Norvig, 4th edition. What are we working on now? We're working on some code. Here's the basic problem. If we go over to the code here, this is the pseudocode that we're going to be working on. And the thing that we really care about is this word problem. Okay. This comes from the algorithms PDF, the pseudocode PDF on the official AIMA website. This is our rendition of it. So you basically just fade out everything that isn't to do with problem and the evaluation function. And what is all, I mean, if we're going to understand code like this, if we're going to be able to read algorithms and pseudocode that take something as ginormous and ill-defined as the English word problem, we're going to have to cure that illness in the definition. And that's what today is about. Look, I'll be honest, I'm still getting used to this. I've been learning this stuff as fast as I can, and I might make a mistake or two. So just prepare yourself. Disclaimer: in math and artificial intelligence, I should not be your master in either. Okay, so what's the problem? Like, if we're going to we pass things to functions in Python as the implementation language that we've been using, and then we're going to continue to use. We pass an argument to a function, but what the heck is this? I mean, it's easy to pass a number, right? It's easy to pass a variable to a function. How do you pass a problem? Okay, well, we're gonna look at that right now. So first we have to get our minds around what a problem is in this context. And don't ignore just focus on the formalizing search problem. These are the components that are going to have to be. Our problem is going to be an object. If you're not familiar with object-oriented programming, I'm not going to be able to teach it to you quickly enough to make this segment time cost effective. So but the basic idea is you create a category of thing that you can keep in memory, and then anytime you create a specific instance or so class or object, instance and object are synonymous, I think. That object, that instance of the class, has to have inherits all of the properties and methods. It inherits all the essential defining aspects of that category of thing. And then you can do specific things with that particular object. So it's like there's the class of oranges, and then there's this particular orange. The class of oranges is roughly spherical, usually orange, or let's say they have to be orange for them to be in our official computing class of oranges. And they don't weigh more than a pound and don't weigh less than an ounce. All of those things apply to our particular orange, which has a particular weight and a particular shade and it has a particular shape and all that stuff. Okay, that's object-oriented programming. We're talking about things in info data we're going to put in memory, but we're going to put some constraints on it so it doesn't go wild and we don't have to specify everything every time we talk about an orange. Okay, that's more or less object-oriented programming. A problem in our pseudocode is going to be an object. Really, just about everything in here is an object, and if you get to the right level of the software or the level of abstraction. But that's what's going into our function, and then we just run lines of code that are control structures and little manipulations on that object. The F over here is the other argument that our best first search algorithm is going to take. This is the evaluation function that we're going to use to prioritize where we go in our search in our search tree of the state space, to use the official fancy terms. Okay, so let's focus on problem. You see how many times it gets acted on in this code. These are two separate functions. So this is the expand node function, and this is the best first search. This is the one. This is the major function, and then this one gets called expand. Is where here? Where? Where is it? Oh, geez. Maybe it doesn't run inside this function. It doesn't matter. Okay. So these are the aspects. These are the things we're going to have to specify in our problem object in code in Python before we pass it to our function. Okay, so we could write this. Actually, let's just go look at it. Here. Okay, this is an implementation in Python. This is an IPython notebook, so it's kind of a little bit different from what we've shown so far. But this is an implementation of best first search by the AIMA people, the AIMA students and faculty, junior faculty, I assume. Come on, unhighlight. Oh man, stop it with the highlight. Why is the highlight so freaking wacky? All right, and this is what it looks like in code, but this does not show the code for the problem object. That's up here. It is a class. It's defined as a class up here, and these are the attributes and methods and sort of things that apply to it, and instructions on how to use that class. Talking about it's going to be pointless. It's going to be much easier to just do it in code. But first, we have to understand, what do we need to specify in our particular case for this particular object that we're going to what do they say? I keep forgetting the verb that they use. You do what? Create an instance. You subclass it if you create a subclass. No, I'm not forgetting anything. I just lack confidence in my code speaking ability. All right, so the problem has these elements: state space, the set of possible states that the environment can be in. This is listen. I'm not being clear enough here. If we say we have a problem and we are writing Python on the basis of pseudocode in AIMA4e, we are talking about the technical definition of the word problem. We are not talking about, my shoulder hurts. I'm not making enough money. I just feel bad all the time. Those are not the problems we're talking about. We are talking about well-defined, well-formed technical problems that we can encode using object-oriented programming in Python or Java, but we're going to do Python, okay? So when we say problem, we should say problem, maybe in quotes. Don't think, oh, my shoulder. No, think state space, initial state, cost function, action cost function. All right? Do those thoughts, not the ones you were having about your shoulder. Okay, so what are the things we're going to have to specify when we write our problem in Python code? The state space, the set of possible states. Okay, that'll be a set. The initial state, that's the state that the agent is going to start in. The goal states, what defines success or solution of the problem. It's a set of one or more. You can have one or more goal states. You don't have to have just one. What should you be picturing? You should be picturing this. Picture you're starting. This is from AIMA. This is their first example, and this is the problem to which this best first search is applied. We're back in Romania. We're going from Arad to Bucharesti, and we want to use a search algorithm to find a path from here to here, and not just any path, but the best path. Okay, the best first search path as defined by our algorithm. So from Arad, you can go to Zarind, Tima something, and Siba something. Okay, you can go to 3 different places, and eventually you're going to make progress across that state space, and you're going to start to draw a tree. Okay, this is your search tree, these dark red lines. This is also from the AIMA people. They helpfully publish their figures as well on their website, so we don't have to worry about copyright infringement on the book, because the book people will come after you, but the website people won't. This is a search tree, okay? And we're going to talk more about that, but that's the AI. The reason I'm not talking a lot about that, I'm not going in deep into the problem, because we're not working on the AI problem yet. We can't. That's for later. That's going to happen in January. This particular problem we'll work through in January. We just want to get to the point where we have the confidence to encode it, to write it in Python, or to understand it if it's already written in Python. Okay, so these are the sorts of things you should be picturing: moving through a state space and drawing a search tree. Okay, so we've got the state space, the possible states, the initial state where we're starting, the goal states where we want to end up. Maybe it's one place, maybe any of a number of places would be good. and we use the isGoal method. That's a programming. It's like a function within an object is a method. Well, again, I'm not going to like talk it to death because just seeing it is going to be much easier, and my vocabulary isn't up to talking it very well. Up to talking it very well. That's exactly how you say that. Actions. Okay, what can the agent do? This has to be specified. So given a state, what actions can the agent do? And it should return a finite set of actions that can be executed on that state S. A transition model describes what happens when you do an action on a state. So the result of an action applied to a state is the transition model, or that method, I guess we would call it, returns a new state. And then the action cost function, actions aren't free, so an action on state S, action A on state S yields action S prime, and it gives the numeric cost of applying an action. And the way you should think about that is just, I edited them out for our purposes, but imagine there are little numbers along each of these edges. Those are like, let's say, the miles and distance. Let's say every action that you take has a cost in miles. Okay, so this way, you're going 100 miles, and this way you're only going 30. So this one's cheaper, but what really matters is the total cost to get to Bucharesti, not any one particular edge or action cost resulting from a transition. Okay, so the action cost function. Oh, also distinguish the action cost function from the evaluation function, which is this thing here, this F that we'll talk about separately when I understand it or understand how to explain it. And then the objective function, which we talked about with gradient and partial derivatives, where we were scoring our. So in this case, we want the minimum sum of action costs when we traverse the state space. That is, but the best first search algorithm, my understanding of it is that this evaluation function only tells us which nodes to expand next. It doesn't tell us. It's not. Oh man, all these terms. Ooh, almost closed my thing. It's not an objective function the way we were talking about it before. It's sort of like the objective function of a particular set of nodes, or a way of what it does is it orders, it sorts the frontier so that we know which node has the lowest cost, so we can open that one up next. It's just one way of doing best first search. Is just one algorithm for searching a state space and looking for a solution. There are other approaches to it. This is not like the only way to get from Arad to Bucharesti. Okay. But anyway, those are the things that we're going to have to specify when we talk about encoding a problem in Python: state space, initial space, goal states, initial state, goal states, actions, transition model, action cost function. Okay, and that's it. That's all I got right now. I'm going to get to the code as soon as possible, so that you can see this in action, so that I can see it in action, so that I can learn it, and then we'll understand it better. Right? Good, great. Okay. All references will be in the PDF notes, retraice.com, retraice.com. Notes.retraice.com is another way of getting to the notes quickly. And there's no code here, but AIMA4e.retraice.com takes us to our companion, and then we have our GitHub, and then there's all these places you can go after this fun little time you just had. All right, same time. Well, today was a doubleheader. I think we're going to do another doubleheader tomorrow if I can pull it off. So it'll be 10 p.m. tomorrow. Eastern, but this slot will be the same time. You don't care what I'm talking about. All right, signing off.